what do we mean when we say bare metal? We'll cover kind of the environments we run stuff on, whether we can actually try and make sense of the term bare metal in this day and age. And we'll, just for fun, we'll look at some, CPU architectures. It's a bit early for that, but, hopefully it will be fun again. And maybe we can try to make sense of all the marketing around bare metal and see if we can actually appropriate it for, 2019. And then hopefully that will provide us with a bit of a segue into embedded systems, small devices. And we'll talk about the different classes of devices that we have these days, what sort of software stack we run on them. And particularly, we'll look around devices you'll probably have in your house, different classes of devices you might have in your house, and really how we program them, because traditionally it's just C, but it's not really. And then if you have time, we'll talk about the one true bare metal. So let's go. So bare metal, by the traditional definition of things, is your application just running directly on hardware. Your computer executing instructions directly without an operating system, without any abstractions. Whatever machine code gets generated out of your code runs directly on the CPU. But we can't really, if you think of the applications you kind of build today, does any of them really fit into this term? Yet we see bare metal on cloud now. We have bare metal cloud and bare metal as a service, which from and actually a bit of a disclaimer while we're here. I put this abstract together in a bit of a kind of moment of rage when I saw bare metal as a service online, because from a hardware perspective that just seems just wrong. But it kind of makes sense. We'll get to that in a second. So let's try to evaluate. Actually, does it make any sense to call anything bare metal? Bit of an existential crisis. So let's try to kind of find a new definition or try to fit it into maybe constraints based on environment, maybe infrastructure, maybe programming language, maybe size of the device that we're running these things on. If you go by the traditional definition of the term bare metal, well, our application should run directly on hardware, nice and easy. But except for very small embedded devices, we don't do this. Traditionally, we do bare-ish metal, where we have an operating system that we run our stuff on. But again, realistically, in this day and age, we probably have a runtime, a VM of some sorts that run our application. So already for a standard run-of-the-mill, software project, we have several layers of abstraction. So definitely not bare metal. Let's go a step forward, and we have the cloudy bare metal, where we run things in VMs and containers, and turtles scenario, where we have a lot of abstractions which make no sense. Please don't do this. So from an environment perspective, the term bare metal only applies to an extremely limited, extremely small, set of applications, which are, again, generally 8 16-bit microcontrollers with no memory or very little memory. Let's talk about infrastructure. So we could potentially say, bare metal, things run on physical servers, etc. Not really, because again, there's software abstractions, but we're fighting marketing here as engineers, so let's pretend to understand what's going on. But except no one really does this, because we have a lot of things as services, and we have virtualization, etc., etc. But remember I mentioned that it all kind of makes sense when we say, bare metal as a service. So it turns out the whole turtle scenario we were talking about earlier, thanks to containers and Kubernetes and all that stuff, we now actually call dedicated servers bare metal cloud. And from what I can tell, it's simply, dedicated servers with a nice provisioning API is now bare metal as a service. So again, marketing is kind of winning there. Is that bare metal? Programming languages is an easy one. You're all familiar with compiled versus interpreted. Theoretically, when you compile something, it just becomes machine code, and machine code runs on the CPU, and it's bare metal, right? Whereas, interpreted languages, of course, not talking about the extremely clever stuff modern VMs and interpreters do, like JITs and all that stuff. They don't. They just take in the high-level user-readable source code and then, produce an output. So, the typical C to assembly, right? So the high-level C snippet that you see on the left, as an intermediate step during compilation, gets translated into this assembly listing. Now, all these assembly instructions, push, move, add, pop, return, these are all machine instructions, right? So bare metal enough? Well, if you were running this on an old architecture, like this is the 8080, one of the first commercial microprocessors, you could argue that, yeah, this is as bare metal as you can get, because the opcodes that gets translated into machine code from the assembly listing would literally translate to some blocks of transistors doing something with them. Except modern CPUs are a lot more complicated than that. And the instruction that you write in your little assembly listing is not actually the instruction that the processor executes. It gets translated into a simpler RISC-style set of instructions, and your CPU actually does a lot of clever stuff, everything from branch prediction to out-of-order execution and all that stuff. So really, even if you write things in assembler and just try to run things on a modern CPU, that's probably not bare metal enough either, going with the original definition. So does it matter? Shall we just, not care about it? Unfortunately, it's becoming more and more of a popular term, bare metal. So I guess, we could try to say in 2019, bare metal perhaps means dedicated servers with a nicer API to provision them and control them. Or another common theme seems to be that things that run on small devices are considered bare metal. So 2 examples I picked, JavaScript and Java on bare metal. Well, except those languages are not designed to run on bare metal. They're small, tiny VMs. And actually on this paper, there's even, the subtitle is the Java virtual machine. So I guess we could just think of bare metal systems as small devices these days, which brings us on to embedded systems. So an embedded system is a little computer system with a dedicated purpose. This term also is a bit overloaded. Your mobile phone used to be an embedded system, but it also does spreadsheets these days, so is it an embedded system? So for all intents and purposes, we're going to go with the traditional definition of the embedded system, which is a little device that is designed to do one thing, and specifically one thing. And just to make it more interesting and not keep talking about theory, etc., we'll try to look at some devices you might have around the house and look at what sort of architectures they use, what software stack they might be using, which programming languages are used for programming them, and generally how these things are put together. Another thing that I try to do is, given that hobbyist and tinkering platforms like Raspberry Pi, like Arduino, etc., are pretty much commonplace in most developers' desks these days, I'll try to put them in the same category as the actual commercial devices that we'll be talking about. So the first device we'll break down is a little home gateway or a Wi-Fi router. So this is the same sort of device as, you can think of Raspberry Pi fitting into this category. So we have, traditionally several hundred megahertz of a CPU. These days, of course, multi-core is pretty much free, so you get that everywhere. Usually you have more than 16 megabytes of RAM. 16 megabytes is kind of a limit of, whether you need to really worry about stuff or not. And then, 4 megabytes or more flash. So it's, development on these are done not too dissimilarly from how you would just generally develop stuff on Linux, except you probably will have to take into account that, well, you might only have a few megabytes of flash to fit your stuff in. And also, you probably are not going to install Ubuntu on this tiny device, except you have like a micro SD card or something. So to make our life easy, we talk about, actually, sorry, I skipped a slide. These devices are kind of fairly capable. They have all the traditional embedded interfaces, as you can think of, like SPI, UART, GPIOs, etc. But also they have stuff that we're familiar with from our desktops, such as USB, such as PCI Express, and so on and so forth. And the memory is fairly fast. It's usually DDR. The main difference is that you can get one of these chips for about $3, and it's a Linux-capable device that can run a lot of very complex stuff in your home. So in terms of software, we mentioned that you're probably not going to run, Ubuntu on a volume device which has 8 megabytes of flash. This is where embedded frameworks and build systems come in. So they provide you with kind of a foundation or like a base layer where you can build on top of. So it's not too dissimilar to the notion of, installing a lightweight, Debian installation and grabbing a few packages and, if need be, packaging your applications and so on. But generally, these go one step below that, and they provide BSPs, board support packages, which takes care of initializing the custom hardware that you have, which you don't generally have to worry about when you are, deploying things on, small Intel NUCs, or, when you're running things on your laptop and so on. There might be specific drivers or device trees that initialize the peripherals, et cetera, in a certain way. And quite often, you'll probably have some patches to make sure everything is running smoothly, and some driver blobs maybe to make sure your wireless, Wi-Fi card is working, and so on and so forth. So in fact, all of these systems have packages. They're similar to, say, how you would package your application for Debian or for RPM distribution. And they also do dependency management, which is great. But the problem generally is that you'll find slimmed down versions of the libraries that you're using if you're resource constrained. And also depending on the architecture you're running, that can potentially cause issues. An example for this is we're running Erlang on a device with 8 megabytes of flash, and on MIPS, which is not necessarily the architecture that Erlang is run on mostly. And we realized that there were a couple of really obscure stuff in the runtime that we had to come in and patch. And the notion of patches is everywhere in these frameworks, and they have very easy ways of keeping track of patches so that you can have reproducible builds, et cetera. So the most common ones are listed below. OpenWRT, you might have heard of it. It started off as a project, a firmware replacement project for, say, your home gateway or modem Wi-Fi router thing. But it's actually a lot more than that. It is very commonly used in a lot of commercial applications that are not just Wi-Fi access points and that kind of stuff. So this is kind of the workflow of Open Embedded. We're not going to go through all of it, but the idea is that the build system is in the middle. That's the blue section over there, and it allows for all sorts of stuff being everything from configuration to all the external packages and their dependencies and so on, and all the heavy work that's required to actually make this work, like cross-compilation environments, SDK generation, and ultimately image generation that goes in a tiny flash memory somewhere that ultimately constitutes your image. So this is a screenshot from the beautiful configuration mechanism of OpenWRT. Curses-based configuration is just very elegant. And it's effectively just high-level categories of things you can just go and basically pick and mix and build your system. So there's a lot of support for pretty much all the small, cheap SoCs, wireless SoCs you might, system-on-chip devices you might find in commodity embedded devices. And they also have a very kind of nice mechanism in which you can define custom profiles based on ultimately the hardware you're using. So, the highest level, ultimately, selection for the platform would be, say, your products. Underneath it, it will be, the kind of SoC you're running, and underneath that will be the general Linux support for that particular set of chips that you're using. So, an example, as I've picked on this screenshot over here, is the TP-Link whatever model of the device. The sub-target is generic because we're not doing any specifications, customizations there. And underneath that, we have the general Atheros platform support. And if you look at the categories, there's everything from mail to multimedia to sound to emulators, and you just go and pick and mix whatever packages you want. And just like these standard packages are put together for you to pick and mix from, you can also package your applications to appear in the same configuration where you can build your applications just alongside all the other standard stuff. So that's the first category of devices. And because there's a lot of people I know in the audience that is very interested in Beam, special mention goes out to the NERVS project, which is, it provides a very, very nice, very slim little base image that you can build on top of. It's effectively just a tiny Linux image that boots into Beam and provides all the tooling niceties around it so that you can just package your application on top of the NERVS base. And they have a great set of devices supported. There's good platform support and a very active community as well. So if you're interested in embedded and if you're doing Elixir or Erlang, definitely go check out NERVS. So the second category of devices I want to talk about is small-ish things, but not necessarily the smallest things. So an example would be a smart light bulb, right? So generally, you're not going to run Linux in these, although there are some smart light bulbs that actually run Linux, which is hilarious. But ultimately, these devices generally have a couple hundred megahertz of a CPU, very little RAM, very little flash. And most often, you would find a small real-time operating system running inside these devices. So what RTOS it might be, it's really hit and miss. It all depends on whether you're using a really cheap, really obscure CPU core and a custom vendor-built RTOS, or the industry standards like the Wind River provided RTOSs, etc. So in terms of CPU cores, generally you'll have something that is either a 16 or 32-bit CPU. Of course, ARM is quite prolific, but these devices are usually mass market products, so usually you find much, much cheaper cores that have not necessarily very commonly found in the Western world when we're just picking devices to build systems with, which also comes with not necessarily the best compiler support, etc. But one signature of these devices is that generally there's some sort of radio attached to it along with the standard set of peripherals. So if you're a hobbyist, if you've done any tinkering with the ESP32 or the ESP8266, we're talking about that class of a device there. It's plenty powerful to do complex stuff, but again, you're not going to have Linux. You're probably going to be fairly restricted as to how much stuff you can do with it. In terms of architecture, again, you have a whole bunch of peripherals on the left-hand side, but notice that there is no USB or PCI Express anymore because we're not in Linux land anymore. And with these kinds of devices, we now have to start worrying about power consumption, and generally, USB and PCIe are not necessarily the lowest power interfaces that we have. So instead, you have things like I2C, SPI, STIO, etc. And as part of the whole package, usually you have some support components, like, say, some cryptographic accelerators, an RTC to keep track of time, because if you don't know what time it is, then you're probably going to have a bad time negotiating SSL. And usually there's a black box of an RF blob somewhere that does something that you never know what goes inside. It's the blobs that we were talking about. It's generally painful. So in terms of software options, this is actually quite an interesting world to be in, because in Linux you can do anything and everything, right? If that's why we didn't spend too much time on it. We mostly talked about the packaging side and the base platform side of things. But in this world, you can actually pretty much run any language again, but you are now in the world of much smaller, much cut down VMs for interpreted languages. So MicroPython is very, very popular. It's It works very well. You're not going to run all the Python libraries that you have necessarily, but if you definitely absolutely want to run Python on a 16-bit, 32-bit device, then yeah, sure. Same goes for JavaScript. The Atom VM for Erlang and Elixir is a work in progress. It's very actively developed. It lacks certain things. Like, I don't think it has binary support yet, for instance, or very basic binary support. But you're in the world of trying to fit traditionally a large thing, which is a VM, into a very small device. But most of these things are fairly usable. Whether you would ship them in production, that's a very good question, actually. The other option is to actually find stuff that effectively compile down to C, or have compiler backends that support the small embedded architecture that you're using. So of particular interest to me right now is NIM, which is a very interesting language. It's fairly sane in terms of the ideas that it has, which make it kind of a good fit for embedded systems. It's not very popular. A friend of mine, Christian, put together a nice SDK and like even a Vagrant box for experimenting with it on ESP8266, which is, if you're interested in languages and if you like playing with these small architectures, definitely worth a try. I am looking forward to hacking on it. Another special mention goes to the Grist project. I don't know if Peter is around, but it's again a small hardware platform and software support built around it, which gives you Beam running on RTEMS, which is a real-time operating system. It's not bare metal, as it's claimed on the website, because again, you're running on top of an RTOS, but it's bare enough metal, perhaps. But of particular interest is that, unlike most of the little VM experiments that we covered earlier, this project has a particular commercial and industrial focus, which kind of separates them from, say, MicroPython or JavaScript. Now we talk about the most interesting class of devices, really small devices. And when we say really small, we're talking literally maybe a kilobyte of RAM, a few kilobytes of RAM maybe. Sometimes, not even any flash storage at all. Or, maybe if it's high volume enough of a product, we might even not have a processor. It might just be an ASIC. So if you're a hobbyist, think Arduinos. They kind of fit into this category where you have 4 or maybe 8 or 16-bit CPUs. Here be dragons potentially. For really low-cost products, think toys that you get for not much money at all. You will have a very obscure chip in there, which probably costs a few cents, but also don't expect good compiler or vendor support for those. But also, again, ARM and 32-bit are becoming quite popular. Actually, an interesting note, so we said they might not have any flash at all. So if it's a processor, how do you get the code inside the device? It may not necessarily have flash storage, but they could be OTP, one-time programmable chips based on fuses. You literally burn the program onto the memory that it has using high voltage, but you can't change the program after that. Or again, based on volume, it could be a mask ROM where your instructions are effectively translated into a photolithographic mask, which is usually the highest level of the chip, and they are hard-coded into silicon effectively. Very rare that you will get to use these techniques. They're usually used for products that are designed to be extremely cheap and sold at quite high volumes. So in terms of software, this is actually the painful territory, because what's considered an SDK in this world is usually just a compiler that kind of works, and also a few examples, and that's it. But having said that, somebody ran Go on an Arduino, which is pretty insane and pretty amazing. And a project I used to be involved in, we ran Occam on Arduino, which is, anybody know about Occam? Yeah, I see some faces. So, that's not to say these devices are boring. You can still do a lot with these devices. It's just that, again, whether it makes commercial sense or not, again, whether you're going to want to ship a product that is running Occam on an Arduino, that's another question, that's another discussion. I did mention chips for a few cents. I wasn't kidding. You can actually buy at 3 cents, about 3 cents, 4 cents microcontrollers these days in quantities of 10. They're one-time programmable. They have very, very limited resources. They have terrible documentation. But actually, if you search for this part number, you can get a processor for 3 cents. If you're interested, talk to me afterwards, because I've been playing with them, and it's a horrible experience, but also fascinating. So, right. Oh, and architecturally, these things, lots of colorful blocks, but they're incredibly simple blocks. So again, no USB, no PCI Express. You have, general GPIO, general I/O. You have things like I2C, SPI, but again, low power, low cost. You're not going to get much. You're not going to put a USB flash drive into these things. Can if you want to, but probably not a good idea. So, okay, a summary of what we talked about. I'm just trying to make sure that we don't delay the other talks. Bare metal as a term doesn't really mean all that much for general purpose computing. And really getting stuck on terminology is, we have far more interesting things to do. But I propose that, just again, because this is a marketing versus engineering battle, in the cloud context, let's just think of bare metal as dedicated servers with a shiny API, so you don't have to interact with any humans to spin up servers. And in the device context, let's just think of it as small devices not running Linux. On the embedded system side of things, there is quite a difference, between what you can do, because you could literally be dealing with a 4-bit CPU or a 64-bit embedded Linux system. If you're running Linux, and if your budget allows for you to have, say, a nice little, 128 megabyte storage, run JavaScript on them. If you do not have that kind of luxury, if your hardware people are forcing you to use an 8 megabyte flash chip, maybe don't use JavaScript. But the point is, you can pretty much do whatever you want, and that's why it's quite nice to be working with embedded systems in 2019. So I'm a hardware guy, and I would feel really bad if I don't mention just one thing about bare metal before I finish my talk. Aside from the microcontrollers, the slightly bigger processors, etc., can you think of any other technology, any other silicon device that we can potentially hail as the one true bare metal system? Anyone? FPGAs? Yes, thank you. So FPGAs are, by definition, the one true bare metal system. If you're not familiar with FPGAs, they are literally, a bunch of logic gates. Of course, they're far more complicated than these days, but it's one step above a custom silicon chip where you can actually program really low-level stuff to perform at really high speeds. If you want, to experiment with your own processor design, you can code up your own processor and run on these devices. So aside from a few specialty blocks, say digital signal processing blocks or memory blocks, these devices consist of what's known as CLBs, complex logic blocks. So the logic description that you write, either in Verilog or VHDL, or these days there are much higher level, frameworks that allow you to have quite nice representations of systems, like Python, for instance, compiled down to FPGAs. You can effectively build your own computer system, computer architecture. You can stuff 20 CPU cores in them if you want. And these devices usually have very advanced peripherals, very high-speed links, and generally a lot of very fun resources you can do a lot of stuff with. So again, we had to mention FPGAs, otherwise I would not be able to sleep tonight. Thank you very much for listening. I think we might have a couple of minutes for questions. If not, I'm going to be around today, so thank you.
Any quick questions?
So you talked a lot about the environments that bare metal runs in. What do you think are some of the most exciting tools to make our lives easier, to make the life of writing embedded code easier, that are coming out in the near future?
In what category of devices would you say you're specifically in embedded Linux world, or?
Let's just say, you know, I'm trying to debug this chip that I've been working on for a really long time. Stuff's not working. I want like, I don't know if you saw GeoHot's new debugger. It can scroll back in time.
Yep.
You know, what do you think are some of the most important developer tools coming out
So
for those tiny systems now that changed significantly from like 90s or like 80s, where
Sure.
you just shove a printf?
So really high quality debugging tools have been around for a very long time. So what you're talking about is effectively a tracer, not a debugger. There are companies that do not publish their prices on their websites, selling, you know, tracers for a very long time now. So there's Lauterbach, which will sell you, you know, a little pod that will debug 100 cores for a lot of money. So unfortunately, that's a very painful world to be in, especially when you get to multi-core and when you're running things like Linux and, you know, debugging those kind of embedded devices. I don't have a very good answer for you, unfortunately. What GeoHot is doing is kind of trying to, let's say, democratize the very expensive stuff that was available to very big corporations, perhaps. But overall, you know, most embedded systems developers, especially ones working on smaller systems, would tell you that printf is the best kind of debugging they have on most systems, which is quite tragic. So trace ports, trace pods, etc. These are all things that probably are the state of art, if you know, like what I mean. It's again, no great answers, I'm afraid. At least that I know of, anyway. So when things run, it's a beautiful world. When things don't run, especially given that you're potentially running on custom hardware, debugging, for instance, DDR3 or like high-speed memory, you know, on a custom board, is probably one of the most painful things you'll ever do. And at that point, you need, you know, a lot of investment in both your physical debug tools and actual software tools that help you debug those as well.
Right. Thank you very much.
Thank you.